Okay, so this video is going to cover velocity and acceleration. Okay, so we're looking at uniform motion initially. Okay, so straight line with equal displacements is what's called constant velocity or uniform motion. Okay, and if we look at the motion map, the motion diagram, the vectors are all equal. Okay, they're going in the same direction. There's equal spacing between the dots. Okay, for the position versus time graph for a constant velocity motion, the graph has a constant slope. The slope is equal. You have equal displacements over every time interval. Okay, the velocity of an object, again, is rise over run. Change in velocity, or change in position over time is your velocity. Okay, and if it's uniform motion, the velocity is constant. Okay, so we can take the rise over run, xf minus xi, position final minus position initial divided by the change in time, and you can rearrange it to get this. Okay, sometimes you will see d's or x's. Okay, so then you can say that if you look at this equation here, we can say that the change in position is velocity times change in time, going from up here. Okay, again, looking at the displacement is proportional to the time interval. All right, so again, if we look at this and the equations, we get our velocity is change in position. Okay, we say that y is proportional to x. They're related in this through this equation. And this is assuming going through the 0 point of your graph. Okay. Okay, so if you double x, you double y. If you decrease one, you decrease the other one by the same thing. This is the idea of ratios. Okay. Assuming it's proportional. All right. So a train's moving due west at a constant speed. So a passenger notes that it takes 10 minutes to travel 12 kilometers. How long will it take the train to travel 60 kilometers? Okay, so we just got to think now we're moving at a constant speed. Okay, constant rate of change of displacement. And we know how long it takes to go 12 kilometers. We can probably figure out how long it takes to go 60 using that proportional reasoning again. Okay, so we kind of look at, we know the difference between 60 and 12 is 5 times. So we're going 5 times farther. Okay, so we know that the initial time interval was 10 minutes. So if we do that, then we can just figure out that if we go 5 times farther distance, we're going to go 5 times farther in time. So we're going to go 50 minutes in time. All right, so soccer player is 15 meters from the goal. She kicks the ball hard. After half a second, it flies past the defender 5 meters away and continues towards the goal. How much time does the goalie have to move into position to block the kick from the moment the ball leaves the kicker's foot? Okay, so we have to think about what we know here. We know that the ball is 15 meters away, okay, from the goal. And it travels that 5 meters in 0.5 seconds. Okay, so we know that. And with that, since it travels 5 meters in 0.5 seconds, 5 divided by 0.5 is moving at 10 meters per second. Okay, so that means that if the defender's 5 meters from the ball striker and the goalie is 10 meters or 15 meters away from the striker or from the player who kicked the ball, that means there's 10 meters between the defender and the goal. Okay, so if our ball is moving 10 meters per second and the goal is 10 meters from the defender, that means it's going to get from the defender to the goalie in a second. Okay, so from the moment that the ball leaves the kicker's foot, it's going to travel take a total of 1.5 seconds to get from the foot to the goal. And if you're confused in that, just listen to it again. Okay, so we know our speed, 5 meters in 0.5 seconds. That gets you a speed of 10 meters per second. And if we know 10 meters per second, and we know that we have a distance of 15 meters. In order to travel 15 meters with a speed of 10 meters per second, it will take 1.5 seconds. Okay, now we've been looking at these velocity versus time graphs. Okay, and we're going to use the idea of area under the curve to figure out, if we're given a velocity versus time graph, how much displacement is covered. Okay, we look at v equals distance divided by time, but we can also say then that the area, distance, is speed times time. Okay, so we can figure out the area under the graph, under a velocity versus time graph, will get you your displacement that you travel during that given time, because distance is speed times time. So speed, your y component, time, your x component. So you're looking at your height with your v, your time of your x. Those two things will give you the area under the curve. Okay, so there's going to be some practice problems for you to look at it for that. Next section on this is what's called instantaneous velocity. An instantaneous velocity is velocity at any given point. Okay. We look at an instantaneous velocity, meaning now on. Okay, from right now. Okay, so we have basically what you can look at is you can draw a tangent line to each of these spots, and the steeper that it gets, the greater its instantaneous velocity is at that given point. Okay. So when we talk about velocity, we're really talking about instantaneous velocity, unless we say average. Average velocity would be like over a time interval. Instantaneous is right now. Okay, so we're looking at the slope of a line. Okay, and we look at this when the velocity changes, because the steepness of this graph changes. It gets steeper. All right, so finding instantaneous velocity. Okay, we have to do very, very small intervals of change. Okay, and again, this one's showing a very, very small portion of the graph right here to look at your change in position over time. Okay, we can look at that and say that we can find that velocity at that given point. Or you can also draw what's called the slope of a tangent line. Okay. And it should be the same value as if we can really zoom in on a given point. Okay. So the slope of the tangent line is the instantaneous velocity at any given time. Okay. So when you have various speeds, you can use the velocity versus time graphs to still find displacement. You're just going to have to change how you're measuring under the curve. Okay. So we're still looking at the area under this curve for our displacement. You might just have to use a different formula and a slightly different formula. You might have to use a combination of formulas to get there. Like for this one, you can use this rectangle and almost a triangle here to approximate. Okay, so again, we're looking at when you use this velocity versus time graph to figure out how far the car moves during this 3 seconds. Okay, now we have a triangle for this one. We don't have a rectangle. Okay, so we're looking at the question is how far, indicates we have to find the displacement rather than the position. Okay, so we're looking for a change in position between 0 and 3 seconds. Okay, now because we have a triangle here, really this can be looked at as a right triangle. And a right triangle, find the area of a right triangle, it's 1/2 base times height. So the base is 3 seconds. The height is 12 meters. So 1/2 of 3 times 12 is 18, as it says up here. Okay, so it travels 18 meters during this first 3 seconds of its velocity. Okay. So that's how you use the area under the curve to solve for triangles. It's just assuming it's a right triangle, you can go 1/2 base times height. Rectangle, base times height. Okay, and it does make sense. Okay, so this one, we're going to go through this a little bit so you can kind of understand what's going on here. So this car moves in a straight stretch road, but this shows the car's position as a function of time. So position versus time graph. Okay, so if we look at this graph, we should be able to answer these questions. At what points do the following conditions apply? Where is the displacement 0? Well, where x is 0, because x is now your position. This is back to the position versus time graph. Okay, the speed is 0 is where we're not changing position. So B, where it flattens out, and E, where it flattens out, your displacement or your speed is 0. It's increasing speed where it's getting steeper. Okay, steeper speed here. It's getting a steeper. Now some of you are saying, well, it's going down. Yes, it's a negative velocity, but it's the numeric value of the speed is increasing because the line's getting steeper, and the speed is decreasing where the line's getting shallower. Okay. Next piece is acceleration. So we've looked at velocity is a rate of change in position. Acceleration is rate of change in velocity. Okay. So the ratio of velocity versus time is the slope of velocity versus time graph, which happens to be the acceleration. So if you figure out the slope of an acceleration versus time graph, you're going to figure out the acceleration of an object. Okay. So meters per second unit for velocity, rate of change in velocity. So now we're looking at meters per second per second. Meters per second squared is your rate of change unit, your acceleration unit. Okay, so this is now saying the Corvette speeds up 27 meters per second in 3.6 seconds. So we have 27 meters per second as it's speed up. So it goes from like rest to 27 meters per second in 3.6 seconds. Okay. So every second the car, so if we take 27 divided by 3.6, we get 7.5 meters per second change is your acceleration. Okay, just to give an idea here, rate of change from 0 to 60 for a couple different vehicles. All right, so now we're looking at how fast they change speeds. Okay, so we're going to look at this lion capable of making a rapid start. So lion can sustain an acceleration of 9.5 meters per second squared up to a second. How much time does it take for a lion to go from rest to a typical recreation around a top speed of 10 miles per hour? Okay, so we have to convert, first of all, 10 miles per hour to meters per second. And 1 mile per hour is about 0.45 meters per second. So that gets us our final speed of 4.5 meters per second. Okay, so the lion can accelerate at a rate of 9.5 meters per second. That means it goes every second it travels, it's going to speed up 9.5 meters per second. Every second it travels. Okay, so it'll take the line less than a second to reach 4.5 meters per second, because it's in 1 second it can go from 0 to 9.5. Okay, so our acceleration is 9.5 meters per second squared, but our speed of 4.5 meters per second is how we determine the time. So we go back to this. Acceleration is change in velocity divided by time. Okay, and we can rearrange it. Change in time is change in position or change in velocity over acceleration. These two just essentially change spots. So our change in velocity is 4.5 meters per second going from 0 to 4.5. Our acceleration is 9.5 meters per second squared. So 4.5 divided by 9.5 is 0.47 seconds, which makes sense because in 1 second, it can go from 0 to 9.5. So it should be just under half. Okay. So that's how you rearrange the acceleration equation to solve for time. Okay, you should be able to do that for a change in speed as well. All right. So again, we talk about the object's acceleration as the slope of this line. Okay, if we have velocity versus time graph, the slope of that line is your acceleration. Okay, so we've graphed some velocity versus time data over here. Okay, And the slope, the rise over the run is your acceleration. All right, so let's look at these two graphs, one that creates the other one. So we have a velocity versus time graph and acceleration versus time graph. In this graph here, our velocity is increasing, but it's increasing at a constant rate. So because it's increasing at a constant rate, its acceleration is constant. And because it's gaining velocity positively, it's going to have a positive acceleration. Now, here, its velocity is constant. Okay, our velocity is constant here. Because there's a constant velocity, there's no change in velocity, there's no acceleration. Okay, and then this one, a negative slope in our velocity is becoming more negative, or not as positive, so it's decreasing. Our acceleration then is negative. Okay, now that's not to say here the object is stopped. It's not what it says. It says the object is going at a constant speed. Here, negative speed. All right, so hopefully you understand that. If not, ask in class. All right, so a ball is moving in a straight to the right, goes down this ramp. Okay, so now if you think of what's going on here, for this first part, it's going in a straight line. Straight line, constant speed. Okay, as it goes down the ramp, it's going to speed up. Okay, it's going to accelerate. Okay, here, it's going to go at a constant speed, which is going to be greater than where the ball started up here. Okay, so the acceleration versus time graph, okay, we're initially going to have no acceleration because at the top, it doesn't speed up. At the bottom, it doesn't speed up. It only speeds up in here. So your acceleration time graph would be a straight flat line at 0 until it got to here. From here to here, it would be a positive, excuse me, its acceleration would be negative because it's going downward. Be a negative constant acceleration, and then once it gets to the bottom here, there's no more acceleration because it's going at a constant rate. All right. So an object can move right or left while either speeding up or slowing down. Okay. Now, if you look at this, so object is going to the right, positive slope. It's accelerating because there is a rate of change in velocity. Okay, now this one, however, we are slowing down. We are slowing down, but it's still a positive slope. It's just in the negative velocity. It's slowing down in the opposite direction, so it still has a positive slope because it starts fast and slows down, but it's going in the opposite direction. Okay. And the reverse is true. All right, so again, let's look at this for a moment. So we're looking at positive and negative accelerations. So A is positive because it's going to the right and it's speeding up. B is negative because it's going to the right, it's going in the positive direction, but it's slowing down, so that's a negative acceleration. Now, C. Somebody like, well, how can C be a positive acceleration? Okay, it's going left, so it's going to the negative direction, but it's also slowing down. It has a negative change in velocity. So you have a negative change, a negative distance to change, a negative velocity change gives you a positive. And D is negative because one of them is going to be positive and one of them is negative. Okay, it's speeding up, but it's going in the negative direction, so you're going to have a negative velocity. Okay, then we move on. Motion with a constant acceleration. So now we're looking at something that's speeding up at a constant rate. All right, so again, looking at this, we can figure out this velocity versus time graph to figure out the slope to get the acceleration. Okay, Now, this is a very important equation. We change acceleration is equal to VF minus VI over t. We rearrange this thing to solve for our final speed, and we have VI plus A delta t. So how much time times acceleration plus your initial velocity gets you your final velocity. Okay. This is a kinematics equation that is going to be used quite a bit during the course of this class. All right, so the velocity versus time graph, if it's a straight line, we have a nice constant acceleration. Now, like the velocity versus time graph, to figure out area, we can do the same thing. Okay, the displacement, we can figure out the displacement here by using the area under the graph. Okay, we can figure out the area under the graph to get from a velocity versus time to get displacement. Okay. Now, because it's divided up into a rectangle and a triangle, we can take it to figure out our final displacement is equal to, if we have some initial displacement that maybe we start with, plus VI delta t, that's this bottom rectangle here, plus 1/2 AT squared, that's this, okay? This is how you find the final displacement of an object if you have a constant acceleration. Okay. So if we're going to combine these other two equations, we get this. VF squared plus VI squared plus VF squared equals VI squared plus 2A delta x. Okay. Delta x is your displacement. Okay, your book does a good job of deriving this equation, and we will do that. We will do some of this in class. But those equations that are mentioned on here, you need to be able to manipulate those. You need to be able to rearrange those. You need to be able to put a couple of them together to figure out certain things. And we will practice that in class. Okay, so when we look at things with constant acceleration, you're going to use these, what are called the kinematics equations, a lot. Okay. So if you know one of velocity and acceleration at time, you can use this one to solve for a final speed. If you're looking at distance changes, displacement changes, you need to look at this equation. Okay. But if we know distance but we don't know our time, because we need the time for the first two, we can use this one. So this is a lot of figuring out what you need, what you have, and what you need. Okay, so you're driving in a car, so just under 35 miles per hour, 15 meters per second. You see a ball roll out in front of you. You hit the brakes and you stop as quickly as you can. And then you're going to say for this one, you come to rest in 1.5 seconds. So we're going to figure out how far you brake. Okay. So we got the graph on the bottom. The motion map shows that you're slowing down. We've got the graph that you go from 15 to 0 meters per second in 1.5 seconds. And you can get hopefully a nice straight line off of this. Okay. So this is what's going on. So we know our acceleration is final speed minus initial speed divided by my time. My final speed is 0. My initial speed is 15. My time is 1.5 seconds. That gets me an acceleration of negative 10 meters per second squared, which it should because you're slowing down. So every second that we're traveling, we slow down 10 meters per second. So that's our acceleration. We need to figure out that before we can figure out our positions. Okay, so we're going to use this, our change in position is equal to VI delta t plus 1/2 AT squared. Our initial velocity is 15 meters per second, given to you in the problem. Our time, 1.5 seconds, given to you in the problem. 1/2, negative 10 is our acceleration that we determined up here. Again, our time is 1.5 seconds, so our distance that we travel is 11 meters. Okay, so if you're going 35 miles an hour, hit the brakes and you stop, okay, in 1.5 seconds, you will travel 11 meters, about 34 feet. Okay. Yeah. All right. Okay, so Spud Webb was the one of the shortest basketball players ever. He could leap 110 centimeters, 1.1 meters off the ground. Okay, so I want you to think about this and figure out how high he would have to jump, or how fast he would have to leave the ground to jump that high. Given that as soon as he leaves the ground, he is slowing down at a rate of negative 10 meters per second squared. Okay. Now, when you look at velocity or acceleration and time, you have to deal with a quadratic relationship. Okay, we're dealing with y is proportional to x squared here. All right. So we're looking at, again, the straight line distance problem here. Okay. How far from the starting line will the car be? Starting at rest, travels 6 meters in a second. Continues that same acceleration for an additional 4 more seconds. How far will he go? Okay. So we have to figure out, initially, says after 1 second, the car has traveled 6 meters. After another 4 seconds, so a total of 5 more seconds has elapsed. Okay, so the initial elapsed time was a second, so the elapsed time increases by a factor of 5. Okay, so our displacement then goes up by 5 squared. Okay, so our displacement is going to be 25, 5 squared, times 6 meters, which is 150 meters. Okay, because of this proportional or the quadratic relationship between our displacement and our velocity. Okay, so hopefully with this, I'm gonna have you pause on these and look at how to solve these particular problems. And this is a big one. Does my answer make sense? Okay. Can you look at pictures? There will be some pictures that you have to draw on the AP exam, some graphs and some motion diagrams. Okay. Okay. So last thing we're going to look at is this problem. We have a rocket that's launched straight up with a constant acceleration of 18 meters per second squared. After 150 seconds, how fast is the rocket moving? How far has it traveled? Okay. So here are our pictures of a motion diagram and a graph. And it's getting farther and farther apart every second. Okay, so we know it starts at rest. We know that its y position is on the ground. It starts from rest at t equals 0 seconds. Then we know our acceleration is 18 meters per second. So then we just have to figure out the final velocities given that our time is 150 seconds. Okay, so we know our initial velocity is 0. We know our acceleration is 18 meters per second. We know our time is 150 seconds. So we know that constant rate of acceleration. We can figure out our final velocity using this kinematic equation. Okay, the distance traveled then would be using this given kinematics equation right here. Okay, we know we're on the ground, so we don't have to worry about our initial velocity, initial position. Our initial velocity is 0 as well. Okay, then we have this acceleration of 18 meters per second squared, and we know our time is 150 seconds. So really our final velocity, in this case, is just going to be 1/2 times our acceleration times our time squared. Okay, so then our total distance that it travels is 200 kilometers, 200,000 meters. Okay, so again, looking at how to solve the problems, you have to figure out what you have and what you need. And really, what formulas are you going to need? Formula or possible formulas to put together to figure out what you need. Okay. Another sample problem to figure out how far it has to go to get up to speed. Okay. If we know our acceleration, we know our final speed, we have to figure out our time. Okay. Then we can figure out our distance traveled. Okay. Again, it's rearranging the equations to solve for what you need and what you have. Okay. All right. That's this video, and there's a lot of information here. I would highly recommend going through this a couple different times, pausing it if you need to, rewinding if you need to, and be sure you ask questions in class. See you soon.